morning, everyone, and thank you for attending my defense titled Harvesting Solar Energy on a Silicon Photonic Chip. As a quick outline, we'll go through the introduction consisting of solar energy and silicon photonics, and then we'll go through the results and conclusion. This circuit diagram will appear quite a bit throughout the presentation, and I'll explain it along the way. Do you know that an hour of sunlight is enough to power all of human society for a year? And yet, solar energy only contributes to 2% of global power. That's because the process of harvesting solar energy is inefficient. If you see the amount of sunlight hitting the surface of the Earth, shown in the graph here, a silicon solar panel only absorbs a part of that spectrum. And so most photovoltaic panels can only be 32% efficient. The reason for that is that the electronic band gap of silicon limits the optical absorption bandwidth of the photovoltaic panel. On top of that, solar panels only capture directly incident sunlight, and so they can't use ambient light or light from other directions. And finally, electricity storage methods require conversion. So even after this electricity is converted from sunlight to electricity, the electricity then needs to be converted to potential energy in dams or chemical energy in batteries, because electrons, being fermions, repel each other and therefore can't be stored. This raises the question, could these electrical limitations be overcome by an optical process? Today, I'll be defending the position that they could. So let's look at what it would be like to harvest solar energy on a photonic chip. Well, first of all, instead of using bound electrons, we could use free electrons, thereby circumventing the electronic band gap. We could use silica microstructures on the top of the chip in the cladding to increase its acceptance angles and couple to ambient light. And finally, photons, being bosons, can be stored as an infinite number of photons in the same state, allowing for extremely high energy densities. And we could use such resonant devices to store light instead of electricity. The platform that we choose for this purpose is silicon photonics. Why? Because silicon is a semiconductor and it's abundant in nature, which means there are already really good techniques to convert silicon into microstructures and extract it. In fact, these techniques are so mature that silicon photonic devices already route 30% of all internet traffic. And the process from going from an idea to a design to a device in silicon photonics is so well standardized that there are two available lithographies to research labs. One, electron beam lithography, allows for low lead times but high resolutions, which is great for rapid prototyping. And once we have a design, that device could be fabricated in deep UV lithography, which is larger lead times but extremely large batch sizes, so great for mass manufacturing. The bottom line is that silicon photonics is cheap, accessible, and scalable. Let's go back to the outline. In the results, we'll discuss our toolkit for silicon photonic device design. I'll then show you how to harvest sunlight into confined optical modes. I'll then split these confined modes based on their polarization. We can rotate one of the polarizations in one branch to match the other, match the phase of the other branch to match the first, and finally combine these two branches into the same mode that couples to free electrons. To begin with, we look at I'll show you how to use photonic band diagrams as a tool in silicon photonic device design. This was done mainly using numerical mode, FDTD, and MATLAB, and combining these tools together. And the paper that I published as a result of the work is shown at the bottom over here. Prior silicon photonic device designs typically employ sub-wavelength periodicity, but they don't optimize the dispersion. And when talking to the device designers, I found that they don't actually know how to use band diagrams to be able to optimize dispersion. And so this presented a valuable opportunity to use band diagrams as a tool in silicon photonic device design. If we look at the effective index of a material, that effective index compresses the wavelength of light, or the effective wavelength of light in the material. Now, if we overlay two materials together, then we can interact with the sub-wavelength. We can interact with light at a sub-wavelength scale. And this creates bands, which can be represented by the photonic band diagram, that typically has about three regimes. The sub-wavelength regime below the light line, the band gap or band stop regime, where no bands propagate and no light can propagate, And then above the light line is the green diffraction regime. If we corrugate these, if we change the refractive index between these two interlaid layers, these two interlaid materials, we can change the refractive index contrast and therefore change the shape of the bands. The reason this is important is because the position of the band indicates the phase velocity of light propagating through the material, and the slope of the band can be used to control the group velocity. And so regions where the slope of the band is almost zero, like around 1310 nanometers, allows for slow light effects, thereby creating resonant devices which could be used to store light. If we extend this to a sub-wavelength grating based device, we could build a 2x2 intensity splitter. We could also tilt the grating to access its two-dimensionality and control its birefringence to build a polarization splitter. And finally, we could use an isotropic grating or a photonic crystal to open up a band gap for one polarization, letting the other one through. These devices allow us to develop a toolkit for dispersion engineering in silicon photonics using the polarization, direction, and frequency of light. We can use this to build a 1x2 or 2x2 intensity splitter, polarization splitters, or use numerical techniques to create typically unconventional devices that maximize either the footprint, the performance, or the bandwidth of the device in unintuitive ways. And then finally, we can look to nature to see how evolution itself creates photonic crystal structures. In fact, this will be the subject of our next study. In this study, we look at how the frustules of diatoms contribute to photosynthesis in the cell. The techniques that we use are shown here, including experimental techniques, and the papers are shown at the bottom left. Previous studies on diatoms only analyzed parts of the frustule. And so they opened up quite a few missing links between the experimental analysis and the simulation work. And as a result, there was no full analysis of a complete diatom frustule. This is what we'd be exploring in this work. So if you look at a diatom frustule under an SEM, I managed to extract the topography of the frustule and therefore create an overall model of the frustule, as you see here. If we zoom into the valve, I can identify certain features. The holes have a certain directional periodicity depending on the direction of propagation of light. The lattice symmetry varies across the photonic crystal, and this lattice seems to have a short range order but a long range disorder, which is really evident when we map the holes into photonic band diagrams. So as you see here, I map the holes into a photonic band diagram for every set of holes in the bottom left graph, and its corresponding density of states on the right shows that an ensembled average of this density of states matches the photosynthetic absorption spectrum of the cell. Now, if I take this valve and study it under 4 different microscopy techniques, I can extract the topography of the valve using SEM and AFM, and I can extract its optical response using HSM and SNOB below. Combining this with simulations of the entire frustule, I can identify certain localized functionalities within the frustule. There's a disordered photonic crystal at the valve, which we discussed earlier, diffraction at the girdle, a cross-section the cross-section of the frustule operates like a racetrack, and it shows butt coupling at the tails. Now, if I combine all of these functionalities into one photonic circuit, I created a model of the frustule, which allowed me to identify 3 harvesting mechanisms: capture, retention, and redistribution. This study was the first full optical analysis of a complete diatom frustule. I used this analysis to produce the first model of solar energy harvesting by the frustule, and then used the model to estimate the contribution of the frustule at about 9.83% to photosynthesis. And now that we know how to, and this contribution could be directly applied to the silica cladding of a photonic chip. Now that we know how to harvest sunlight into optical modes, I'll show you how to split these modes based on their polarization. In order to split these modes, previous designs typically had a large footprint or small features, which combined do not allow for commercial viability. In my design, I focused on the fact that the optical response is based on the geometry of the structure, while of course taking into account the polarization and wavelength. So if we look at how TE light propagates through a waveguide, I can increase the waveguide width to create a multimode interferometer and allow for a self-imaging length, which is the length at which the interference pattern converges, and collect TE light back at that port. For TM light, it allows for a different self-imaging length, and therefore that allows me to separate the polarizations. Now, this self-imaging length depends heavily on the width of the structure. As the width increases, the number of modes increase. It also depends on the effective index, which is more dependent on the polarization than the wavelength. And if I combine all of these together to be able to optimize or maximize the bandwidth of the structure, I noticed that I found that a 3-micron width would be the perfect amount to be able to maximize the bandwidth within the C-band. And so I designed a device using 3 microns width and 67.5 microns length. This device was the smallest MMI-based polarization splitter. It had a large bandwidth and high fabrication tolerance over 72 different variations, as you see in the graph below. And its main limitation was a low extinction ratio, which could be overcome by either cascading the device or optimizing its geometry even further. Now that I've shown you how to split modes based on their polarization, let's try to rotate the polarization of one of the branches. For this purpose, I wanted to design a non-reciprocal standalone silicon photonic polarization rotator. Now, previous designs of polarization rotators were not commercially viable. Essentially, they used magneto-optic materials, which require post-processing steps after the silicon photonic fabrication step is done. Or they require an external magnetic field, which is simply not deployable in the real world. Everyone said that a silicon photonic isolator is not possible, but nobody answered why. And so I wanted to I wanted to answer that through the study. I designed an electromagnetic coil surrounding a waveguide. The waveguide is shown in red. And a current passing through the coil, indicated by the white arrows, creates a magnetic field that passes within the waveguide. That magnetic field rotates the plane of polarization of light in the waveguide as given by the equation VBL, very simply. V is the Verdet constant, which depends on the wavelength as well as the dispersion of light. B is the magnetic flux density. And so I used 3 different waveguides to be able to engineer its dispersion and therefore control its Verdet constant. B is the magnetic flux density. And so I characterized the electric coil based on to see how much and found a linear response with magnetic flux density. However, the resistance per unit length increased exponentially with the current passing through the coil. And that was because of its resistive heating. Essentially, as more current passed through, the coil increased in temperature until it eventually shorted. This was the first horizontal axis coil in silicon photonics and also represented the first design of a standalone silicon photonic Faraday rotator. Its main limitation was an extremely low rotation angle, for which I identified ways to be able to overcome it by orders of magnitude. And now that once one polarization is rotated, let's look at how to match the phase of the other polarization. For this purpose, I wanted to see if it was possible to modulate orthogonal polarizations independently. Now, typical modulators are already birefringent. In fact, the plasma dispersion effect we know modulates TE more than TM because TE is confined to the waveguide. So instead, but the amount of modulation or the difference is uncontrollable. And so we look at the Pockels effect, which can control the refractive index tensor. For this purpose, I looked at the chromophores of electro-optic polymers. Now, really simply, when an electric field is parallel to the plane of polarization, it induces a different phase delay than when it's perpendicular to the plane of polarization. And so if I can use this concept, I extended this concept to design a device that had 3 electrodes, 2 signals, and a common ground. Now, by applying a voltage on these 3 electrodes, I showed the first design of a simultaneous dual polarization phase modulator. It offered a theoretically high efficiency due to the Pockels effect, and its main limitation was the crosstalk. So essentially, I can modulate both phases equally, but if I wanted to modulate one phase without the other, then the maximum crosstalk that I incur is about 1/3 of the phase delay. And that's how I manage both signals. And finally, once the phases are matched and the polarizations are matched, we can combine them into the same mode and then couple it to free electrons. For this purpose, I want to design a device. I designed a device that transfers the energy from the optical mode to the kinetic energy of free electrons. Now, previous designs in this regime were just not scalable. Either they use perpendicularly incident light that induces transverse deflection forces on the electrons, or they need custom structures which aren't reproducible by other labs, or they require complicated setups like a synchrotron facility, which isn't accessible to most research labs around the world. So I designed a device in silicon photonics, which was completely standalone and operable in a transmission electron microscope. Therefore, this makes the entire experimental setup highly accessible to most research labs around the world. The coupling between the electron and the optical mode can be defined by its quantum optoelectronic coupling efficiency, or coupling per photon, as you see in the equation over here. That depends, of course, heavily on the laser. It also depends on the synchronization between the electron and the optical pulse. So essentially, when we overlap the two, the electron needs to match the phase velocity of the optical pulse so that energy can be exchanged between them. And in the overlap region between the electron and the optical pulse, it heavily depends on the electric field, the amount of electric field in that overlap. And so if I maximize all of these quantities, I can get a quantum optoelectronic coupling efficiency of about 0.29, which represents an acceleration gradient of 2.38 gigaelectron volts per meter, or an energy gain of 43 kiloelectron volts. This was the first co-propagating circuit that's operable in a UTEM. It was the first design to optimize quantum coupling efficiency at silicon photonics, and the design showed that we can either maximize the energy gain or the acceleration gradient. Its main limitation was the damage threshold of silicon and the operating constraints of the experimental setup. Finally, in conclusion, I showed you how we can harvest sunlight into confined optical modes, how to split those modes based on polarization, how to rotate one of the polarizations, match the phase of the other polarization, and combine these into a mode that then couples to free electrons. The main outcomes of this work was that I developed a method for band engineering in silicon photonic devices, determined how the frustil enhances solar energy harvesting in the cell, demonstrated a silicon photonic polarization splitter over a wide bandwidth and high fabrication tolerance, designed a tunable standalone silicon photonic Faraday rotator, investigated the modulation of both polarizations simultaneously, and optimized the coupling efficiency between an optical mode and free electrons. Putting all of these together, I propose an optical process to harvest solar energy on chip to show that it could be done. The results of this work are split up into research, leadership or mentorship, and collaboration, as you see here. My main learning outcome was that my idea is much bigger than my plans, and my results are a very small combination of both. The resulting publications are shown here, with one paper under review and one paper that appeared in the press quite recently. The conference publications here, and patents shown here. And with that, I would like to thank my colleagues, without whom this work wouldn't have been possible, as well as all of you wonderful audience members and the supporting organizations and my friends and family. Thank you.